So as he said, my name's Andy Aquila. I'm one of the instrument scientists at LCLS. I've been designing the tender X-ray instrument for about the last year or so now. I want to go over kind of a basic overview because I don't think a lot of people in this community have ever used an FEL, how it works, why it's different from a synchrotron, some of the first experiments we ever done with X-ray spectroscopy here at LCLS. And I want to tell you because we've actually been shut down for the last year. And I would like to tell you what we've been doing in that last year because we have not been, we've been pretty busy. And then I want to tell you pretty much what I think we can do with this instrument, this brand new instrument I've been designing, and also show you some of the interesting and complicated challenges that go into actually designing a instrument. Because this is cutting edge instrument, and it's quite challenging in to get a femtosecond instrument overlap to sub-micron resolution. So this is the LCLS or Linac Coherent Light Source. It's built on the old SLAC campus where they used to have a humongous linear accelerator. Actually, it was the biggest building in California. That accelerated electrons close to the speed of light, and they used to do like electron-positron collisions. And this was running for about 50 years. In fact, when it was built, I think, as I said, it was the biggest building in California, or longest at least. In the last 10 years, actually a little bit before that, they've started converting it to a X-ray laser. And we have an undulator hall, which is similar to an undulator at LBL or any other synchrotron, except it's 100 meters long. We currently use the last 1/3 of the Linac. For reference, this is a freeway that goes over. This is a 280, so if you're ever going from San Francisco to San Jose, you'll pass right over the Linac. It's probably running while you're driving over it. We currently have 2 experimental halls. These are dug under a hill. One is the near hall, used usually for the soft X-ray experiments, and one is the far hall, usually used for the hard X-ray experiments and to get the ultra small focus. Our office building is located here. Just for references. So what makes an FEL different from a standard undulator at a synchrotron? Well, you have your electron bunch going through the magnetic structure, and it's going to oscillate. And in the electron frame of reference, you get dipole radiation, and then in the lab frame of reference, because of the relativistic properties of the electron bunch, you get X-rays generated. And we can completely ignore any electric fields. We just worry about the magnetic fields from the magnetic structure of the undulator. In an FEL, we have 100 meters of undulator. So we start building up X-rays. And these X-rays are actually traveling along with the electrons, and they slip effectively one wavelength per every cycle. And this field starts to actually push and pull on the electrons. And if they're too far advanced, it actually pushes them back a little bit or absorbs energy from them. And if they're too far behind the standard field, it actually pushes them towards it. So what happens is you end up with what's called micro bunching, where the electrons all start to get into these really small kind of pancake-like structures, and they all start radiating in phase because they all effectively radiate at the same phase because they're lined up. So we cannot ignore this E.E term. So now instead of having the radiation proportional to the number of electrons, it's proportional to the number of electrons squared. It's also proportional to exponential with the length. And this turned on, as I said, 2009 was the first light at LCLS. And so it's been running for 10 years. And quickly it showed exponential growth. Gets to a saturation region. It doesn't, we can go up a little bit higher, but at some point you start actually you're limited by the electrons reabsorbing the X-rays. You can taper your undulators, but when we first turned on, we did not actually have very much K value to actually adjust the undulator parameter to taper it. So we had a saturation. Typically, depending on photon energy, this was anywhere from 1 to 5 millijoules. These things are very spatially coherent. That was actually one of the first experiments done at the LCLS. And they measured, I think it was 78% of the energy was in the TEM00 mode. So this is a laser. The pulse length can vary from about 100 attoseconds or 0.1 femtoseconds, all the way up to 200 femtoseconds. You can try to make the electron bunches longer, but doesn't typically laze as well. And as you go down below 10 femtoseconds, we have to do tricks. So the amount of power you get out, or the millijoules per pulse, scales kind of linearly with pulse duration. And right now we are operating at 120 hertz. We're still operating at 120 hertz right now. So the instruments we have, actually, you can scratch the first two off. My hutch is now where SXR, or Soft X-ray Research, used to be. So that's my space now, my domain. And AMO is now considered what's called TMO, brand new hutch, which they ripped everything out of these the first two hutches, and it was a construction site for about 6 months. The fundamental properties of the FEL, now it used to go from 1 kV or a couple hundred EV up to about 12.5 kV. We actually now have two undulators, one going from about 1 kV up to 25 kV, and the other one going from about 2 kV to 5 kV. It is still a 120 hertz machine for the moment. We can get in. I'll get into that after the break of how it's not going to be that anymore. As I said, the pulse durations are in the 10 to 50 femtosecond regime. We can get down to attoseconds if we really wanted to. And we get 10 to the 12 photons, or millijoule level pulses out of the machine. And this is great. When we go through the process of actually selecting proposals in the PRP, they are instructed to look at three things. Can it be done at a different facility? And if not, can it be done does it use the coherence? Does it use a temporal length or the femtosecond nature? Or does it use a peak brightness? And the third thing they look at is probably, can this be publishable, or how high quality it is. Those are the three things, like most facilities, but we really focus on what unique properties we have, and those are the pulse duration, millijoules, or the number of photons per pulse, and the coherence. You'll notice also, because we have a new undulator, that the hard X-ray undulator is now vertically polarized. This was done with respect to actually making our crystal optics more efficient in the machine. So what can we do with it with respect to X-ray absorption spectroscopy? Well, one of the first experiments that was done at the SXR beamline, and that was to take a surface of ruthenium with a carbon monoxide gas and pump it with a 400 nanometer laser. And this was, let's say, back 2000, I think this was done 2011. And they were able to actually see remarkable differences before, when the X-rays came before the laser, and when they came afterwards in the X-ray absorption. And even in the emission spectrum, they were able to see these differences and attributed them to different bonding structures in the molecules. And they were able to confirm that they could break CO on a surface. Well, if you can break a molecule, how about forming a molecule? So they did a very similar experiment, except they took CO and actually wanted to form it with free oxygen on the surface. So the experimenters looked at the oxygen edge, and they looked at very specific regions in it, so that they knew for a fact, based on synchrotron measurements, they could figure out where the bonding was for the oxygen, the near edge, and the CO, and the single oxygen by itself. And they actually plotted this as a function of time delay. And you'll notice our time delay went from 12 picoseconds to 0.25 picoseconds, or 250 femtoseconds. And they were able to actually see the oxygen change, see the CO bond change within a few hundred femtoseconds, up to, and the fully formed molecule within about 800 femtoseconds to a picosecond. And they actually were able to figure out, based on this, where on the surface the oxygens were on the and what the distances were separating them, and how it actually formed. And this is pretty cool. I don't think before this I saw any XAS experiments with this type of time resolution ever in my life when I first saw this. And I started out at this ALS back as actually a summer intern. And my first experiments there were actually measuring transmission of thin foils of various materials, scandium being particularly one that I remember getting my first paper on. And if someone told me they were going to be able to do time resolution at the instrument I was working on, I would have never believed it. But here, this is done on a daily basis. In fact, our time resolution is far better now than it was when we first started doing these measurements. And it's just really impressive what we can do these days. When I was a PhD student, I was actually working on XMCD with high harmonic generators, trying to make circularly polarized harmonics and measure the X-rays magnetic circular dichroism, mostly at the M edges, which are a little bit more messy than the L edges. The reason we were trying to do this was back in the 90s, a paper came out that kind of shook up the magnetic community, where I don't remember who the first author right now, but they took a laser and heated up a metal surface and then did visible light magnetic spectroscopy and imaging on it, and found the magnetization fell within a few tens to hundreds femtoseconds. And this, based on the theories of magnetization at the time, should not have happened. It was very controversial, and it took a while. The ALS worked on this. With Light Source worked on this. They used slicing undulators, and they were able to show that this is true, but they were not able to get any time resolution, just that you can demagnetize the sample really quickly. So, of course, one of the first experiments was we got a new delta undulator, which is very similar to our undulators with the same period, except it has 4 magnetic poles, and it can actually make circularly polarized light. And if you put it at the end of the long undulator, because you're in the exponential gain regime, you can actually get very high powers of circularly polarized light. And we did this. We put it through the SXR machine, had the grading, scanned the L edges of iron and gallium, and we compared those to the ALS, perfect match. And we actually did a pump beam, a laser pump in the magnetic field, and you can see the results. We're getting much better in our time resolution now. In fact, what not shown in here is actually a timing tool, which I'll explain, I think, in the third part of the lecture. And this is the normalized signal for various magnetic materials, and it does fall really quickly. And now we're developing theories for why this is and how to work with it. Two really critical pieces of equipment that we've learned are necessary is to block a fraction of the beam. And using a silicon nitride, we let the beam transmit through it. It absorbs a bit of the light. Soft X-rays absorb a lot more than a bit. And we have a microchannel plate here. We use this for I0. The reason we need I0 is every single shot the LCLS is different. It's unique. You can be 1 millijoule one shot, 0.5 the next, 5 the following shot. It jitters. The jitter is usually about 30%, but what's also an issue is it jitters in your frequency domain. Because you really have the lasing effects happens on really attosecond spikes. You get about 10 or 100 attosecond spikes in the pulse, and it can vary plus or minus 10 eV at the soft X-ray range. And you may actually be on one shot, get 100% transmission through, because you hit one of the spikes, you get a huge transmission. Another shot, you get 0 transmission. So how do you normalize this? Well, you can take an average. We have some gas monitors upstream. We can try to average those, but those do not resolve the spectrum. So we need a I0 after the monochromator. Otherwise, it's almost hopeless, or we can't see really small changes. And to see XMCD, we need really small changes. Another thing we learned is to let the spot diverge and to use a CCD of some type and put filters of known thicknesses where we pre-calibrate those. If we try to use most detectors at FEL, all the photons come at once. If you're using a Pilatus, it's going to count 1 photon because that's how it's designed to do it. If you're using a CCD, it's a little bit better, but you still get 10 to 15 photons per pixel. And at 120 hertz, that can build up quite quickly. So if you're doing, you have to read out shot by shot, or you have to be able to attenuate so that you can build up a strong signal. There are some limits as well, and this is something that I've been working on for a little bit now. And at the 100 nanometer focus at TXI, I was just looking at germanium, and a paper came out in Japan, from Japan, that actually have multiple ones now, that they claimed they can actually do 2 photon absorption. So we figured we'd try it. And what you do is you come in, germanium has a K edge of 11.1 keV. You can come in with a 6 keV, or in this case, a 7.1 keV photon. And you actually get 2 photons to absorb and kick out an electron from the K edge. And then you're looking for the 9.8 keV fluorescence. And as you change the power, this is a quadratic signal. It's not linear, meaning we actually do get enough photons on the surface to actually do this. I don't think that this is a FEL effect that's very interesting. So we're not just saturating; we're getting enough photons to actually do two photon absorption. Now, is that interesting? It could be. If you want to do magnetics with a K edge, you could do magnetic circular dichroism with a K edge now, because you can go from an S to a D transition because of the selection rules, which is pretty cool. At the same time, I can tell you that I had a fairly thick, I think it was a millimeter thick germanium crystal, and after about 10 shots, half the crystal fell off because you really crack the crystal. You're doing enough, you're putting enough photons to stress the crystal to actually drill a hole every half millimeter. You end up, it ends up just cracking right along the crystalline planes. To get all these shots took a long time, to be perfectly honest, with the repetition rates we're doing, but it is quadratic. But you have to be careful. If you put too many photons on your sample, that could be a problem, at least on the 120 Hz machine. So there's also, we do a lot of X-ray emission, especially with crystallography. We actually have enough photons so we can do the crystal diffraction image on a single shot, but also collect a spectrum almost on a single shot. The problem we've seen is we have to be very cautious about the polarization and also about the fluence. We see very subtle changes in the spectrum with polarization, and we also see dramatic changes with polarization. The reason for this is you can get a single atom can absorb one photon, have an Auger event or a fluorescence event, then absorb another one, but the electronic state above it's changed. So and the core hole lifetimes are in the femtoseconds. So if you absorb multiple photons and emit multiple photons within this time frame in your molecule, you're changing what the electronic state of the molecule is. So you have to be very cautious about how you interpret the electronic transitions. It's very telling at 40 femtoseconds where these should all line up, but they don't. So the emission spectrum can change. And this is something that's pretty important. And we've designed a new machine to try to get around this by going to a more CW mode of operation. Still keeping the femtoseconds, still keeping the beams TEM00 mode and the coherence, but really going to a high repetition rate, lower fluence machine. But lower fluence is all relative. So before I end the question answer period for the first break, I want to tell you 2 recent developments to kind of stimulate the next section. The first is an experiment that I helped carry out at TXI on manganese chloride, among other manganese salt solutions, liquid jets. We cranked up the intensity, and what we wanted to do was to make this thing laze. And this has been done at gases and other things at LCLS for a while now. But the special part was we wanted to actually tune our undulator, so we actually is the first part to be resonant with with a K beta emission, and the other part just to cause a core hole in the 1s, so 50 eV above or 60 eV above the ionization. And the question was, could we actually see this K beta lasing? Because typically the K alpha just purely dominates. You get enough photons out that it dominates. And turns out the answer is yes, but same time, which not perplexingly, but same time we get K alpha, we actually get K beta that actually has strong shots. This actually correlates more to the beam shape and the intensity and fluence than it does to anything else. It just means we actually have a lot of absorption going on in the sample. But this is an interesting idea. Can we actually do experiments and do not just simulate emission, but can we do multi-X-ray photon experiments? And that's something we should think about. The other is, as I said, we had a lot of issues with I-zeros and normalizing our signals. And a lot of times when we're doing X-ray absorption or X-ray transmission measurements, we had to actually use fluorescence as an I0 measurement, or to calibrate what our total emission was, and it really has been an issue. So we've at LCLS and SLAC, one of my collaborators, has developed this. It's a zone plate XORed with a grating, and the cool thing is it makes it makes actually three foci. One is a 0th order, which we typically block, but one we can actually put through a sample, and the other we can just put through a substrate or just let it be, and depending on how you're doing calibrations. And we end up with 2 actual intensity spots on our detector, on our camera. And we can actually go in and we can actually count the number of photons. As you see, there's some with 10 or 15 photons in each pixel. And we can count the total charge in both, and we can divide them. And the great news is, on a shot-by-shot basis, this type of technique allows us to, on a shot-by-shot basis, normalize what data we have with a monochromator. It solves all the jitter issues we've had, and it gets us really great results. So with these two developments, I would like you to think about what can we do when we have 2 undulators of very different photon energies and potentially cross them. And with that, we can take a break for questions.
All right, thank you. I'll encourage everyone to type in their questions while I'll ask a few. You mentioned blowing up your lovely germanium crystal too quickly.
Yes.
That, of course, is a common problem. I'll send you pictures when I blew up mica, which, of course, exfoliates and is quite spectacular. But the more interesting thing here is would be to study magnetic molecules. In solution, for example, it'll be flowing, you're not going to blow them up. How bad was the count rate? Do you have to be looking at a solid pure element, or is it conceivable to do a two photon absorption experiment on a metal organic flowing in solution?
I think it's very conceivable. The one thing you would want to do is, in this case, I just had a titanium foil in front of a diode. Large, I think it's an AXUV 100, so a large centimeter by centimeter diode. If we put we can either put a spectrometer actually to look at it, or we could put an area detector and collect a huge, large solid angle, much bigger than what I was collecting. So if with 100 nanometer focus of TXI, that's very doable.
I see. So, very interesting. Another question. I really like the stimulated emission work. My question for you is, what is the energy bandwidth over which you get the stimulated emission? And secondly, could you have moved that band to the valence to core region, which is usually very, very weak, and amplified that? The valence to core is much more interesting for studying chemical dynamics, is why I ask.
I believe you could. We actually did. We only had so much. Right now we changed the undulator to a variable gap undulator, so that gives us a lot more flexibility. When we first did this, the K variation is like 0.05. It was really small, so we tuned it so that we were able to see something we knew was a little bit brighter. For the first experiment we wanted to do this on. But yes, you could tune it to the valence, and that is something I know a lot of like Uwe Bergman is very interested in. We also seen some narrowing of the lasing peaks of the K alpha. We've seen chemical shifts when we did this in different manganese solutions. So chemically, we could definitely do a lot of new spectroscopy with this type of technique.
Very interesting.
Hope that answers your question.
Yeah, no, it definitely does. Being able to increase the intensity in the valence to core would be really fascinating. All right, you should continue. Thank you.
Great. So I want to tell you about how we've upgraded the machine, what's coming online when, and the science cases for the TXI instrument. So we were down for a year, and that was to gut the first third of the Linac. So, and we now completely gutted it, and it's still being installed. It's almost fully installed with cryo modules. We were about to finish when COVID hit. Cryo plant was already operational and started the commissioning, so that all stopped, and now is about 6 months delayed. But we wanted to go to superconducting accelerator. The reason to do this is to go to very high repetition rates, almost a megahertz. It's actually, I think it's 969 kilohertz. So let's call it a megahertz. So we can actually do a lot of interesting science with almost a CW machine with these evenly spaced out. And there's a 4GV Linac. We actually have a high energy upgrade plan to go up to 8GV at some point. We currently are going to plan on throttling the X-ray power and the bunch charge to get 200 watts of X-rays on the system. We actually have to be limited by either the electron dump or the X-ray stoppers and how much power they can actually handle, which is kind of amazing. But we're going to go from very similar peak brightnesses, but our average brightness is going to go up 4 or 5 orders of magnitude, which is just huge. This was taken in January when I was working in the beam dump area to install some equipment. This is what I can do. On the right, you see the soft X-ray undulator. On the left, you see the hard X-ray undulator. And behind me, you probably see my cat. Sorry about that. You'll notice the hard X-ray undulator is actually, as I said, rotated the polarization. The magnets are sideways, which means the electrons go vertically. Compared to the normal undulator, you see a synchrotron, which has the magnets vertical, which means the electric field's going horizontally. Now, this is a picture I can take. I'm not a very good photographer. This is what a picture what the LCLS PR department can take. A lot more awesome than what I can do. But even more awesome is last week we got first lasing on the hard X-ray undulators at 120 hertz. This was actually with the first 10 undulators in. They slowly add them in one at a time, making their K value correct. And you can actually see the lasings just starting to turn on. We were able to get to 1.5 millijoules very easily. And we're going to operate at 120 hertz for next year while we learn how to accelerate with the superconducting accelerator. And we were learn how to do that. So both the soft X-ray undulator and the hard X-ray undulator will be operating at 120 hertz, or we may actually split them 60-60 or 30 hertz on one, the rest on the other. That's sort of operational mode. Said we have both the undulators commission and the superconducting accelerator to commission. So that's the current plan. As for the instruments, we have 5 new instruments coming online staged, TXI being the last of the new instruments coming online. The first is going to be pretty much an older instrument that we are recommissioning, LAMP in the what's called the TMO hutch, which is hutch 1 now. The next will be LJE, which is a liquid jet spectrometry experiment. So we actually are able to move the get a new monochromator, much bigger one too, about a meter long mirror on the mono, and actually kick the monochromatic beam upstairs. So we actually now open up a brand new large area where we actually can put a RIC spectrometer with about a 5.5 meter arm RIC spectrometer, going up to 1.3 kV. 3.5 keV with a few micron spot, which is pretty impressive. That'll be the 4th instrument come online. The 2nd instrument is going to be DREAM, which is a cold trims reaction microscope looking at gas phase chemistry. My instrument, the tender X-ray instrument, is going to be the last come online. And what we're trying to do is something very unique with this instrument. We have 2 undulators, and actually, I'm sorry, this was an old slide. I just realized my hard X-ray undulators polarized the wrong way. We have 2 undulators though. And I was tasked with figuring out if we could actually overlap them. So after designing all the X-ray optics and figuring out where to put the mirrors, and then they're being told here's where the hutch is going to be, the answer is yes. We're going to overlap a soft X-ray undulator going from 200 to 5 keV with a hard X-ray undulator going from 1 to 7 keV. So we're going to do multi-photon experiments. We'll be mostly focusing on aerosols, liquid jets, but we can also do cryo temperature samples and some fixed targets. But to be honest, if you're going to do nonlinear spectroscopy, it's probably going to be an aerosol or liquid. We have a forward scattering detector collecting up to 60 degrees, ideally up to 10 kilohertz. They've demonstrated up to 5 so far. And we need really tight foci, 1 micron to 10 micron. Why do we need such a small focus? If you want to make sure you get a photon from each undulator on the same atomic system, you really need to have a small focus. the cross section, for example, if you take a hydrogen beam and you take the cross section of hydrogen at 100 eV and you spread that over a micron, you would need, and you want to make sure you hit every single hydrogen atom, you would need about 10 to the 12 photons. So you really need a micron spot, preferably a little bit smaller, but that actually gets kind of hard in the near Hall. You really, as I'll explain in the next and the third part of this talk, why it's rather hard to get smaller than a micron beam. The crossing angle is about 95 milliradians. I think it's 96 point something. So this is 5.4 degrees. If you take, if you want to know what that's like, take your arm, reach it all the way out, up your finger, and blink your eyes. That's about 5.4 degrees. So that's the parallax if you're curious. Some people who want to do imaging, we're curious what that is. As I said, the photon energies, we're going to go from about 200 to 5 keV on the soft side with harmonic rejection, full harmonic rejection between 1.25 and 5 keV. On the hard X-ray side, harmonic rejection goes from about 1.7 to 7 keV, and it goes from 1 to 10 keV as a goal. In reality, because of the mirrors, we'll probably do 10 keV, but we'll probably choose 1 or 2 photon energies and have a stripe on our KBs with a multi-layer. Just that's how life is with the angles we're talking about. As I said, the mirrors can handle up to 200 watts. We'll try and go for 90% efficiency with transmission of the system, so really high power, 70% of nickel coatings. And we're hoping for a 1 micron spot. The system was designed for 0.7 by 0.93 micron spot. And the beam position stability we're hoping for is 10% or 100 nanometers. And we're hoping to synchronize these to better than 5 femtoseconds, if not even better. So what can we do with this? This is a slide from any nonlinear laser textbook. Will show you what multidimensional four-way mixing is. And we can do this now. We can think about doing this. Okay, K1 and K2 will be on the same vector, but you can actually get 2 pulses down one of the undulators and get a pulse from a third. So we can actually think about timing these different pulses up and doing multidimensional spectroscopy and looking for a different signal. And now this is not as far-fetched. Fermi, which is a soft X-ray facility, has done this at about 100 eV. They've taken a silicon nitride sample, they've taken their pulse, they split it with a mirror, just half a pulse at the mirror, half the pulse not, and they focus it down with an angle between them, and they're able to make pretty much an intensity grading on the sample because these are coherent beams. And that intensity grading leads to an electron grading because you have free electrons on the surface of the silicon nitride, and you can actually send a visible light pulse off and diffract from it, and actually see the diffraction peak from this grading. So it peters out, and how it actually, the time after how long it lasts tells you a lot about how electrons are in this case in the conduction band. It can tell you a lot about other how electrons are in other ways too. And it's just not transient gradient, but any nonlinear technique you've heard of using a Chi-3 process or a third order susceptibility, we could probably do. There's also another class of experiments that's related but to spectroscopy, but completely different. Now, we always have in the past used a laser to pump the system or to trigger a reaction. Now, imagine if we didn't have to do that, because let's say your catalytic converter, or it's not triggered by anything, it's just a continuous reactions. So let's say we had an aerosol jet with catalytic particles, some nano catalysts, and we have this in a gaseous environment where we're triggering some reaction. Let's say we heat it up. So let's say we collect a lot of data at a 10 kilohertz, where we have a spectrum from it, and we have a diffraction pattern. Let's say spectrum we collect just a femtosecond before, so the atoms don't really have time to move. So now, can we do a couple of things? We can actually look at the spectrums and sort the pulses by the spectrum, and then correlate the diffraction patterns and sum up all the diffraction patterns and get a full diffraction image based on the spectrum. So we can actually now figure out how the spectrum relates, so electron states or electron dynamics, how that relates to the atomic positions. Do the atoms move? How far do they move? And better yet, we can now take these particles and let's say we can actually figure out if they're all identical particles. They don't have to be, but they're all identical. We can figure out if 70% are in one spectrum state, 20% are another, and some fraction are in a third, we can actually make a movie, or at least make an energy landscape of where the average default state is for these chemical reactions. We don't necessarily have a time coordinate per se, but we have an energy coordinate where we can actually plot the energy landscape of how the chemical reaction moves through this energy landscape. And we get the full atomic positions. So we can make a movie without actually even collecting time resolved data. And that's pretty impressive. And that's something I really want to explore. So a kind of a hard X-ray probe and a soft X-ray spectrum. Another thing, actually I have two grad students working on this, is stimulated Raman. Raman is a technique used at most synchrotrons. It's used for looking at low Z elements and bulk samples. Very powerful, looking at batteries, lithium. I've heard it being used on flames. And if we can come in and with a hard X-ray pulse and a soft X-ray pulse the delta is equal to the energy loss, we can stimulate that reaction and get all of the Raman signal going in one direction. And this means instead of taking hours to collect a single measurement, or days in some cases, as I've seen, you can now think about actually rastering a sample or doing a time delay of some triggered reaction. So you can actually look at how electrons move in, off of lithium in batteries, or look at how the lithium actually moves in the battery, depending on the battery cell. So really cool stuff. One thing we've also been thinking about is X-ray cars. Can we actually get enough photons on the surface or on the sample to actually do a cars measurement? Coherent anti-Stokes Raman spectroscopy, where we actually, the great news about cars is it's actually the K vector is completely off from this pump in the probe, so you don't actually even need to normalize it. You just collect that signal and you find the ratios of the two intensities coming in. So on some samples where you probably can crank your pulse up to 11, you could definitely do this. So that's type of science we're looking at. One of my favorites is what's called multi-core hole correlation spectroscopy. Now this will require very, very short pulses, sub-femtoseconds, as I'll get into. So I'm just giving you an example. We'll probably never use this system, but we can think of other ones. This is nitrous oxide. We can think of titanium dioxide if you want. The energy bands are interesting and the material itself is interesting. But imagine coming in and kicking a 1s electron out of the oxygen and clicking up to a pi state. So just the near edge. Now, let's say within a femtosecond, you come in with a second pulse of a slightly different energy that corresponds to nitrogen kicking to the same edge. You will actually get, they will actually may interfere because you're trying to address the same state. That state may be occupied, but if you have a different time gap between them, you can actually figure out a lot of interesting information about the system and how actually excited electrons in that system actually move. Mukamel has written a paper about this more than a decade ago, predicting that we could do this, and now we can. We can actually see molecular orbitals and think about actually how to actually try to get core holes to actually address the same orbital and see what that means in terms of absorption. There's another actually interesting technique, and this is done a lot at LCLS because we do have such powerful X-ray beams and powerful lasers here. And there's an instrument called MEC, Matter Under Extreme Conditions. And they typically pump the system with a visible light laser and probe with an X-ray beam of some intensity. And they want to see how to get pressures and densities as in the core of Jupiter. But we can think about actually pumping with soft X-ray. So imagine going to a silicon K edge, or just above it, having a tampered material so we actually can try to get really high pressure, so some carbon film, graphite, diamond on one side, or diamond. We can actually get almost full absorption in the silicon layer for a very thin sample, and almost nothing in the carbon layers. So you can actually get a really high intensity, almost, well, it's exponential decay, but a very uniform pulse fluence. In fact, in carbon, you actually, if you wanted to, you can actually almost from the front of the system to the back of the system get a very uniform intensity because your X-rays don't interact with carbon very much in these energies. But you can do a lot of absorption of the material in the specific layer you want. And they've done this at something similar to this at Aquila, where they did the same trick we did about splitting our undulator. They have a variable gap, so it makes it a little bit easier. But they came in with a pump pulse at 9.8 kV and a probe pulse at 9.6 kV, and they were looking at this, just the diffraction peak and watching how the diffraction peak for this 9.6 decayed effectively with time up to 300 femtoseconds. And then they actually investigated the pulses, investigated the holes they made in this case I think it was just a silicon target, to figure out what they did, what they were doing to the atoms there. Mostly they're actually doing damage to the sheets of the atomic planes, and it's kind of fascinating. But one thing we do at MEC a lot, this instrument, is to technique was done at with titanium, titanium K alpha emission, but to actually do Thomson spectrum, where you come in with a monochromatic beam and you look at Thomson scattering and you look at plasmon formation, so pretty much shifts in photon energy because of your Thomson scattering just near the Rayleigh site. And this is kind of cool. The reason they do it at 5 kV is that was what they were doing at NIF, so they were able to correlate our experiments here with the experiments at NIF. But we at LCLS-II can really go to 5 kV with the TXI instrument. It's its wheelhouse, so we can actually do these type of experiments where we're actually ionizing or getting really high energy densities with a lot of electrons in a material and scattering off of them, looking at the plasma formation, looking at plasmons, looking at other things in them. But we have to be rather cautious. I had a now he's a grad student at Stanford, but I had a summer student work for me last year. And you usually give summer students some fun work. In this case, I wanted him to model just Thomson scattering with two fields. This is something I thought would be a good starting project for him. And what he did was pretty neat. This upper pictures are showing the intensity, which is the length of the arrow, and the direction of the electric field. Center is straight on. This is down on the bottom. Up is up. Left is all the way to the left side. Right is all the way to the right side. So this is looking at the forward scattering hemisphere. And down here you can see the electron trajectories, and you can actually count them. I think he chose in this case 4.2 to 1 kV. In this case was 2 point something to 1 kV. I told him to change it not to be exactly on period, so you don't have to worry about the phase. But I figured this was a great introduction project. He could model it at just F equals ma. I can test his skills, and then give him something a little harder. But what I noticed was that this didn't follow the same path. It actually, as you can see, it's actually shifting slightly as it progresses. And I scratched my head about that, saying that doesn't make sense to me. I was expecting it to be just a sum of two Thomson scattering, E1 plus E2. And then you square it, and they're not going to interfere. But that shift bugged me. So I actually asked him to do a Fourier analysis on the upper, bottom part, the center part, left and right. And he came back, and it wasn't monochromatic. It actually had some indifference frequencies in one direction, but not the other. And I said, that can't be right. So I went home, spent about 2 days on the weekend doing this by hand, because I'm kind of old school, and actually, this is actually semi-analytical. And after a lot of crumpled up paper, I actually found out he was right and I was wrong. It's not the sum of two, because if you have these two beams crossing, you have to remember there's a k.r term. And because the two beams are not collinear and they're cross-polarized, there's going to be some slop back and forth in that term, and it's going to actually end up, if you do the k.r term out, you end up with cosine omega 1 inside your exponential for omega 2. So you end up with a beat pattern inside there, which gives you, if you do the Fourier transform of this, you get some difference frequencies. So just even looking at Thomson scattering, we're seeing something we have to reinvent. It's a small effect, and you can actually modulate it by E1 and on the frequencies, but it should still be there. It's something to actually even look at. And this, I thought, was pretty neat. And he actually spent a lot more time investigating this effect for his summer project. But these are things that I want to simulate you of actually what's the possibilities are to do with TXI. And it's a brand new field. We are looking at nonlinear X-ray spectroscopy, something that has never been done before. And with that, I think it's time for another break and for questions.
That's really fascinating. I'm going to ask everyone to hold their questions until the very end because we're running a little bit late on time.
Okay.
And so why don't you get through the third part and then we'll come back. I see, for example, there's questions about 2D mapping and whatnot, but I want to make sure we get through the lecture
Gotcha.
before people have to get going.
Gotcha. So this
Okay.
last part is where I put all the technical details because it's very fun to think about all these things, and but I'm actually either the fun person, the person has to build this stuff, or is responsible. So this was a picture I took in, I think, just before December of last year. This is my hutch. It's completely empty. Actually, there's now a beam pipe going through it. There is a lot of equipment because they're actually using this as a prep area for hutch 1, the first hutch to come online. My annotation goes there. Right now we have designed and built, and it's going to be shipped here soon, the KB optics, which I want to talk about, and the diagnostic stands, which actually I went in last week, and it's been most of the components have been delivered, this huge piece of granite. TXI is coming online beginning of 2023. That's the time frame. The other beam instruments have shifted a little bit, but we do have some. This TXI was limited by actually our a number of engineers we have at the facility and the desire not to hire any more for a short term because that's kind of not fair to do to people. So we are still coming online in 2023, early science in the middle of it, and PRP or proposals from everyone going to be towards the end of it. So we have a few years to go. So we're in the process right now of starting the end station design, but we wanted to make sure we got the optics all lined out and installed early because it's just cumbersome to actually go on the front end to actually do this otherwise. We've also kickstarted a detector program. This is also one of the reasons we were pushed out to the last instrument because detector research, as if anyone's ever done it, knows that these take years. So we want a detector that works at 5 megahertz, if not 5 kilohertz, if not 10 kilohertz. That's tricky. We want it to be able to count up to 10,000 photons per pixel. That's tricky. We also wanted the 4 megapixel pixel camera, also tricky. So this is the development at LCLS in the TID group. They've actually been able to make small chips with a sigma delta ADCs, analog digital converters. And they've actually are testing these with high repetition rates. Right now they're testing at 5 kilohertz, and they believe they can go up to 10 kilohertz. You'll see a little T here for tender. That's because unlike the big brothers, which I will eventually have, the tender has a different capacitor to optimize it for tender X-rays, centered at 4 keV. This is the one that's just been installed at MFX, macromolecular femtosecond crystallography. It has a beam tube in the center, and this is, I want to say, a 4 megapixel version dedicated at 120 hertz to at 8 keV. So detectors are an important thing. We'll be using small, like 2 tile modules for spectroscopy and spectrometers as well. By focusing optics, as I said, we really want to have really small foci. So, and you want them to be overlapped. And making a 1 micron spot and making 2 of them that overlapped meant we had to be one close to the end station because you're effectively taking a 50 micron beam spot, which is electron size, or the X-ray size, and from 100 meters away, and mapping that with a simple lens equation down to your focus. So if you wanted to actually be a 1 micron, you really have to be close, a couple of meters away, gives you a small Rayleigh length. But we also worry about the vibrations. So we have a huge piece of granite. The mirrors actually deflect upwards first and then horizontally, so we can actually get the mirrors closer into the focus. We were actually not limited by 2 meters by actually how close we can get into the KBs to the sample chamber. It's really how the mechanics of actually holding the mirrors, how close they can be with the I0 monitors attached to them. So actually swapping the pairs, so the horizontal deflecting mirrors are downstream is what we did. We have some diagnostics on the same granite block, so we know exactly where the beam's coming in repeatedly. This design means that any vibrations, any drifts, the beams will drift together, except unless you have really high frequencies, so then we have a butterfly mode. But that's we should be able to damp those out. So this large piece of granite, having the mirrors side by side like this, really is what we've gone for. Fairly conservative idea, but it makes our spots so we feel comfortable we can actually do this. These have to be Bender mirrors, because if you do the KB equation, if you change the angles to get the overlap, you change where the focal position is, so you have to change the radius of curvature because the focal length is r theta over 2. We wanted the shape to be really nice, so we actually these are tapered with look like I-beams. So when they bend in a nice ellipsoidal. We also had to look at the coatings. We chose nickel and boron carbide. Boron carbide's hard as rocks; you can't damage it, and has a 90-some-odd% efficiency. On the hard X-ray line, we go up to about 4 and a bit kV. Angles are a little bit smaller in the offset mirrors in the front end. We needed 2 offset mirrors to get out of the front end enclosure that was required, and also just to overlap in the center of the hutch. We had to go up to 10 milliradians on the soft X-ray side, so that those cutoff energies are a little bit lower. The efficiency on the nickel goes up to 70% on the hard, and it peters off about 7 and a bit. We were looking at going to tungsten, but after a quick calculation, it's quite clear we'll melt that. Even the nickel, if going on this slope here above 7 kV, it's dubious if we will actually not melt the sample as well. These are high 200-watt beams. That's lower fluences, we probably can get away with it. To keep everything aligned, I said we have this huge piece of granite. It keeps our profile monitors, which we have looking at the beam at all times, and a wavefront sensor. This is very similar to a Hartmann sensor, except we take advantage of the coherent properties. So we use a Talbot plane. So we make a smaller grid pattern of holes, so a checkerboard pattern, and we use the interference fringes to repeat, effectively making a Talbot grading on the scintillator. It's wavelength dependent, so we have to move the grading a little bit depending on the photon energy, but it gives us much higher resolution, and it gives us a much better chance of getting a very small focus. These have really changed how we align beams at LCLS. We used, as I said, use the 2-photon absorption of the TXI to remove astigmatism for the 100 nanometer focus. That did not remove third order. Turns out our focus was about, most of the time was twice as big as it had to be. These type of systems can actually give you really great foci. And having them on the same piece of granite means the same thing. They drift together. The cross vibrational modes should be almost negligible. How do we generate 2 pulses? Well, we could do that. We have a photocathode, so we just double pump the photocathode with a laser. But there's a couple of catches here. We have to be on the a multiple of the frequency of the RF, so that and make sure that there's no wake field or other field effects from the first electron bunch. So we have to separate by 5.4 nanoseconds. This had us to, we had to develop an ultra-fast kicker, which meant a very fast switching system where we can actually dump a lot of current and a lot of charge onto 2 metal plates. So the electron beam goes through and it gets horizontally deflected, either hard or soft. And we need about 5 to 10 of these, depending on the geometry, to actually separate these 2 bunches within about a nanosecond, because we really want these things to, this kicking field to be for about 5 after the first one passes. You want to wait a nanosecond, turn it on for a few nanoseconds, and it takes a little bit to die down, and then you want to be able to kick the other one. We're kicking the hard X-ray first. The reason for that is we can make a delay line out of crystals. The idea is we have 4 crystals, 5.4 nanoseconds. That's, because I'm American, about 6 feet. Foot per nanosecond. If you're in Europe, or Asia, that's about 2 meters. So by adjusting crystals, I initially thought, well, we can only move the first or the second and third crystal on the hyperelliptic trajectory, and we can go from low energy to high energy and do all sorts of delays. Our engineers looked at that and said, well, how about we linearize everything? And this is our current design. We have to trade off between what's our maximum delay, can we actually get more delay out of electron bunches if we adjust that, versus the photons. Also, the first crystal, we agreed it had to be water cooled because you're going to melt the system otherwise. Second crystal has to be boron doped, actually not water cooled, but liquid nitrogen cooled, because of so we had to boron dope the second crystal to get the beam on the same trajectory. Otherwise, the trajectory would be off. All the things you don't think about when you're initially saying, oh, it'd be cool to overlap these 2 pulses. Then we start looking at crystals. And crystals, as I feel, they select out the temporal coherent part of the X-ray beam for an FEL. And what I mean by that is they adjust your bandwidth. And the equation for bandwidth is very simple. It's effectively a constant over the number of reflecting layers plus another constant for penetration length. The reflectivity, you can actually calculate out. It's pretty much a reflectivity of each individual layer times something that's proportional to the absorption beta and times the number of layers. That's the good news. And you can combine these equations, you end up figuring out what your reflectivity is as a function of what pulse duration by making crystals thinner. And you can think about actually the really easy formula if you have a Gaussian pulse is the thickness of your crystal over twice the speed of light times the angle is approximately equal to your pulse duration. So if you really want to do a femtosecond experiment, so really look at the core holes, we need to actually change your design to a 2-crystal design, which we're investigating right now. And it's only going to be 10% efficient, but 10 to the 12, okay, 10 to the 11 photons, that's probably going to be good for most experiments. We also realized we had to go from silicon to germanium and not even diamond. And the reason for this is actually quite counterintuitive. Usually you want high reflectivity from these crystals, so you actually go to a thick crystal. We have high penetration, low absorption. But because we're doing thin crystals, we want as many electrons in each layer as possible to actually reflect and scatter the beam. So if you actually just do a 500 nanometers germanium and silicon, which have a very similar D spacing, so I'm only changing the angle here by 2 degrees, you can see the germanium just clearly outperforms the silicon. If there's anything like lead crystal, that's a perfect lead crystal, I would use it. But unfortunately, I think germanium is one of the few materials where we actually make perfect crystals at that thickness. How do we find T0? This is actually work from another student I had, and we were racking our brains, and we came across zinc blend materials, specifically gallium arsenic. And they have a diamond-like crystal structure, except it's not exactly there because gallium and arsenide have 2 delta electrons of 2. So the 200 and 222 peaks are weak. So what I had my student do was to actually say, well, what happens if we do an L3 ionization and just kick an electron out? What does the wave functions look like? So we dutifully used Hardy-Fock and calculated them. And we noticed there were some changes. I said, okay, what does the scattering factors look like? So he calculated them, and they're pretty small differences from what the gallium versus ionized gallium, but they're there. And we can ionize it with 1.1 keV. So what happens if we go to the 4 keV or 5 keV pulse afterwards and look at this? And the answer is at 200, we double. If we ionize every gallium atom, we actually double the the reflectivity of the 200 peak, and we actually get some 1.8%, 1.8 times growth in the 222 peak. We don't have to do every atom. We can do 1% of the atoms and still see the signal. And the beauty of it is the coral lifetime of this material, which is also very cheap, is a few femtoseconds. So we actually get really high overlap. We can actually get this down to within a few femtoseconds, which is pretty darn cool. So this is what we're planning right now of one of the first experiments, just to see this works, 2, to see if we can actually use this as a T0 measurement to actually get the overlap in the sample chamber, and 3, what happens afterwards? Where does the electrons go? Do we have a shake-up process? What does that do to this Bragg peak? Do we actually see the atoms move? And we want to see how to investigate that on longer timescales. Because I asked him to challenge him to do those things, and he looked at me like I was crazy. Turns out I asked a few theorists, and they all told me that no one's ever calculated this sort of process before with multiple shakeups and what actually happens in these type of materials with its energies. Still a work in progress is synchronization. So actually, once you find T0, we want to make sure these 2 beams are synchronized. So what we do nowadays is we have what's called a timing tool. And we collect a lot of data, and we actually collect a timing signal that corresponds to data. And the data is collected out of order. So it's like filming a movie back, last scene first scene last, and then in post-editing, moving the scenes around. We do the exact same thing. We actually have a visible light pump that comes in this a sapphire crystal, make a continuum chirp spectrum. We send the FEL pulse through a silicon nitride membrane. This makes a lot of, doesn't damage the membrane, but it makes a lot of photoelectrons on the surface. So the material goes from being transmissive to being almost metallic-like. And we actually can see that very sharp spot where it actually reflects, so it doesn't actually enter the spectrometer. We can also just put a camera behind this, an image, and if we tilt the screen, we can get a very sharp line, and this will jitter back and forth depending on when the X-ray hit versus the optical. And by rebinning this data, we're able to get, in this case, 20 femtosecond, looking at a bismuth crystal sample and looking at the phonons, 20 femtosecond time resolution. We've actually gone down to 6. Now, pushing it past 6 is going to be hard. Not only that, pushing it to 2 beams is going to be even harder. So we can try a cross correlator. We have a beam splitter that splits into 2 beams, going through each silicon nitride membrane, do a spectrometer. In truth, we'll probably actually interfere these before going to a spectrometer to get very much higher resolution, because we really want to get down to the femtosecond regime for TXI, because core hole lifetimes are femtosecond regime. And if you really want to do any core hole experiments, we need to be in that regime. So with that, I will conclude. Sorry I was running a little bit late, but TXI will overlap 2 different pulses, very vastly different photon energies and sub-femtosecond and sub-nanometer accuracy. I think it's going to enable a new class of X-ray techniques, nonlinear X-ray science, and I'm welcome to, if you want to talk about proposal experiments, I know it's a few years away, but I'm happy to talk about them and hope everyone submits one. It'll be really, really interesting and unique experimental opportunities. So thank you very much, and I'll be happy to answer questions.
Thank you. That's fascinating. There's a couple of questions, especially from an earlier part of the talk. So when you had the stimulated emission from the manganese solution, was it? How low in concentration do you think you can go and still get the stimulated emission? Is there a nonlinear process associated with the concentration of the manganese?
We actually did, we were working with molar solutions. So this was not something that would be standard. And if we go to high repetition rates, I think we can get down to probably millimolar solutions. I honestly don't know how low we can go. Currently, that's actually what's one of the limiting factors of this stuff. And when we first saw it, it's just far easier to see these with single shot, because we're looking at single shot spectrum. And for the simulated K beta, because it's a weaker seed pulse, we actually integrated over a lot of shots before we could see anything, and then realized we actually had a signal. So we've done molar solutions. We can probably go into 100 millimolars. I think it's probably, with our current capabilities, easy. Going to the single-digit millimolar is going to be a little bit trickier currently. But with the high repetition rates, this is one of the benefits, because we can integrate over a lot more shots.
Okay, thank you. Yulia, did you have a question?
Yeah, Andrew, first of all, thank you very much for promoting our work. I think you showed some data from mine and jury paper. And so question here, you mentioned you look, because this is only manganese 2+, and you mentioned you look at high oxidation states samples, because here what is happening is we have this more multi-photon absorption. We see like it looks like oxidized. It looks like more like manganese 4, and I'm wondering, if you start with manganese 4, how it's going to look like.
Oh, that's a good question, and I honestly don't know how it's actually going to look like. And I think it's going to be electronic state dependent, especially when we get these multi-photon photons. We actually have seen where we've actually hollowed out atoms before. We did that on an iron sample at TXI with 100 nanometer focus. So if you start with MN4, I honestly have to think about where the electron cascades go, and I honestly couldn't tell you, but it's probably going to look like MN6, or it may stay like MN4. It really depends on how the energy transfers through the system.
But you do have experimental data, yeah?
I personally don't, but other groups I've worked with do. And this was collected about 2 years ago. They haven't published it yet. So I know others have been working on this. Besides the photosystem 2 groups, I should say, we've been working on, because that's why the MN is such a popular atom to study.
Yeah.
But I know they've experimental data from some matter under extreme conditions groups on iron and other metal type samples. But that's pure metals. That's not really applicable to, I mean, chemistry is a little bit simpler, I should say.
Okay. Yang Ha, you had a question? Are you there?
Yes. So yeah, I'm interested in the NO study. You show a 2D map. And
Yeah, that was actually simulation work.
oh, that's simulation.
Yeah, just from Saul our Mukamel, his group. He did that a few years ago. No one's actually been able to do this type of experiment just yet. And it's one that I saw from his research where it's a little hard to understand the paper a little bit, but I want to try this at some point. Try to see if we can get the electrons in these states. But this is just pure theory.